Hey everyone, and welcome to another deep dive.
Right.
Today we're going deep into the quantum realm. We're talking Bell's theorem and the EPR paradox.
Oh, yeah.
We're going to try to untangle how Bell's theorem challenges our very understanding of reality by showing the potential for non-locality in quantum mechanics. Are you with me?
Absolutely. It is a fascinating journey into the heart of quantum mechanics and what it tells us about the nature of reality.
Okay, so let's set the stage first with this EPR paradox.
Okay.
It sounds like something straight out of like a sci-fi movie or something. What is the deal with this thing?
Yeah, so the EPR paradox, it was a thought experiment, and it was proposed back in 1935 by Einstein-Podolsky-Rosen.
Okay.
And they were really questioning some of the very strange predictions of quantum mechanics, especially when it came to entangled particles.
Entangled particles, that sounds spooky already.
It is spooky. It's like two particles that are linked together in such a way that their fates are intertwined, even when they're separated by huge distances.
Whoa.
So imagine, these particles are flying off in opposite directions, and quantum mechanics suggests that if you measure the spin of one particle, you instantly know the spin of the other, no matter how far apart they are.
Wait, so measuring one particle instantly affects the other one, even if it's like light years away?
Right.
How is that even possible? It seems like it's breaking the rules of how fast information can travel.
That's exactly the point Einstein called this spooky action at a distance, because it seemed to contradict our everyday experience of cause and effect. If you kick a ball, it moves because you kicked it. But this seemed to be saying that something could happen over there because of something that happened over here instantly. And so to try to avoid this seemingly impossible connection, the EPR paper suggested that quantum mechanics might be incomplete. He said there might be hidden variables at play.
Hidden variables, what are those?
So think of hidden variables like secret instructions that are carried by each particle that predetermine the outcome of the measurements. So it's like these instructions are already set even before you measure them, so the particle's behavior is already determined, and that would preserve locality and causality.
So hidden variables would explain how the particles know what to do without needing that spooky instant communication.
Exactly.
But then why not just find these hidden variables and prove Einstein right?
That's where John Stuart Bell comes into our story. In 1964, he came up with a brilliant way to test this whole idea of local hidden variables. We call it Bell's theorem.
Okay, now we're getting to the good stuff. How did Bell propose we test for these hidden variables?
Well, he took this philosophical debate that had been going on and turned it into a testable mathematical problem. And that's what's so remarkable about his contribution.
Okay.
He derived a set of inequalities that any theory relying on local hidden variables would have to satisfy.
Yeah.
So if experiments showed that these inequalities held true, that would support this idea of hidden variables.
Got it.
But if those inequalities were violated, then something else must be going on.
So it was like a showdown between these local hidden variables and the weird predictions of quantum mechanics.
Exactly.
Whose side did the experiments take?
Well, fasten your seatbelts, because the experimental results actually violated Bell's inequalities.
What?
Which seriously challenged this idea of local hidden variables and suggested that nature might be inherently non-local, meaning those entangled particles could be influencing each other instantaneously regardless of distance.
Hold on, this is blowing my mind. So if the universe allows for non-locality, are we saying goodbye to Einstein's ideas about the speed of light being like the ultimate speed limit?
Not quite. Non-locality doesn't allow for faster than light communication in the traditional sense, because while the outcomes of measurements on entangled particles are correlated, they are still probabilistic. So we can't control what those outcomes will be, and therefore can't use this connection to send a message faster than light.
Okay, so no instant messaging with aliens across the galaxy just yet.
Right.
But still, the fact that the universe could allow for this kind of non-local connection is mind-boggling. What does this mean for our understanding of the universe?
Well, that is the million-dollar question, and it has puzzled physicists for decades.
Yeah.
Because it challenges our very fundamental understanding of cause and effect and forces us to grapple with the possibility of a reality that is far stranger than we ever imagined. It even has implications for one of the cornerstones of physics, Lorentz invariance.
Lorentz invariance, it sounds intense. What is that and how does it relate to all of this?
Lorentz invariance, it's a fundamental principle in physics that states that the laws of physics should be the same for all observers, regardless of their relative motion.
Okay.
However, If we accept non-locality as a real phenomenon, it could imply that there might be a preferred frame of reference in the universe challenging this cornerstone principle.
Wow, we've gone from spooky action to potentially rewriting the laws of physics, but I
Yeah.
can't wait to hear more about the implications of all this.
Yeah, it really is a fascinating rabbit hole to go down. The fact that Bell was able to take this seemingly philosophical debate and turn it into something experimentally testable is really remarkable.
You're right. It's incredible. But I have to admit, even though I find this stuff super interesting, the math behind Bell's inequalities kind of makes my head spin a little bit.
Yeah,
Could you break it down for me and our listeners in a way that doesn't require a PhD in physics?
absolutely. The core idea is actually pretty straightforward. Bell's inequalities set a limit on how much correlation you can expect to see between measurements of two particles if those correlations are solely due to those hidden variables we talked about earlier.
Okay, so if the experiments show correlations that are stronger than Bell's inequalities allow, then that would mean hidden variables can't be the whole story.
You got it, and that's exactly what we see.
Hmm.
The experimental violations of Bell's inequalities tell us that the correlations between entangled particles are just too strong to be explained by any local hidden variable theory.
So does that mean Einstein was wrong? He was a pretty smart guy after all.
It's not so much that Einstein was wrong, but rather that his view of reality, at least in the context of quantum mechanics, was incomplete. You have to remember that Einstein was deeply skeptical of some of the implications of quantum mechanics. He strongly believed in locality and causality, and this spooky action at a distance just didn't sit right with him. He felt that there had to be a more intuitive explanation.
Yeah, it is hard to let go of those intuitive ideas about how the world works.
Yeah.
But if we accept that non-locality is a real phenomenon, what does that tell us about the nature of reality?
That is the million-dollar question, and it opens up a whole new way of thinking about how the universe is put together. It suggests there might be deeper, more fundamental connections between things than we previously imagined. It's as if the universe has this hidden network, a cosmic web of interconnectedness that we're only beginning to glimpse.
It's almost like the universe is playing a giant game of connect the dots, and we're just starting to figure out the pattern. But you mentioned earlier that there are other interpretations of quantum mechanics that try to hold on to the idea of locality. Can you tell us more about those?
You're right. There are alternative interpretations like Bohmian mechanics, for example, which try to maintain locality, but they often come with their own set of complexities and challenges. They might preserve locality, but they might also require introducing other concepts that are just as mind-bending, if not more so.
So it seems like we're trading one mystery for another.
In a way, yes, but that's the nature of scientific exploration. As we delve deeper into the mysteries of the universe, we often uncover even more profound questions.
It makes you wonder what other incredible, strange things might be out there just waiting to be discovered. Speaking of which, you mentioned Lorentz invariance earlier.
Yeah.
Can you explain that concept in a bit more detail?
Of course. So imagine you're on a train moving at a constant speed and you toss a ball straight up in the air from your perspective on the train. The ball goes straight up and down. But to someone standing on the ground, the ball would appear to be moving in a parabolic arc because it's also moving forward with the train. This is an example of how motion is relative. However, the laws of physics, like the laws of motion that govern the ball's trajectory, should be the same for both you on the train and the person standing on the ground. That's the essence of Lorentz invariance.
Okay, I think I'm following, but how does this relate to non-locality and entangled particles?
Well, if non-locality is real and entangled particles can influence each other instantaneously regardless of distance, it suggests that there might be a preferred frame of reference, a sort of universal ground from which these instantaneous influences originate. And this would challenge the idea that all frames of reference are equal and could potentially break Lorentz invariance.
So we could be talking about a fundamental shift in our understanding of how space and time work.
Exactly, and that's why Bell's theorem and the EPR paradox are so significant. They not only challenge our understanding of quantum mechanics, but also force us to reconsider some of the most fundamental principles of physics.
It's incredible to think that something as seemingly abstract as entangled particles could have such profound implications for our understanding of the universe. But let's bring this back down to earth for a moment. What's this? So what of all of this for our listeners? Why should they care about Bell's theorem and the EPR paradox?
Yeah, that's a great question. I think there are a few key takeaways here. First, it reminds us that the universe doesn't always play by the rules we expect. Our intuition about how things should work is often based on our everyday experiences, but the quantum world operates in a fundamentally different way.
Yeah, it's a good reminder that we shouldn't be afraid to challenge our assumptions about the world. Sometimes the most mind-boggling discoveries come from questioning what we think we know.
Exactly. Second Bell's theorem highlights the deep interconnectedness of the universe. Even things separated by vast distances can be linked in ways we are only beginning to understand. It's a reminder that we are all part of a much larger web of existence.
And it makes you wonder what other hidden connections and surprising relationships are out there just waiting to be discovered.
Absolutely. And finally, I think Bell's theorem is a testament to the power of human curiosity and our drive to understand the universe. It all started with a thought experiment, a what-if scenario, but through careful scientific inquiry, we were able to turn that thought experiment into a testable theory and then into groundbreaking experimental results that changed our understanding of reality.
It's a reminder to never stop questioning, never stop exploring, and never stop being amazed by the wonders of the universe.
Yeah.
So if our universe allows for this kind of non-locality, what other astonishing things might be out there? What other secrets are waiting to be unlocked?
That's the beauty of science, isn't it? We're always on the edge of the unknown, peering into the darkness, trying to make sense of the mysteries that surround us. Maybe there are even stranger phenomena out there than non-locality things that would completely shatter our current understanding of the cosmos.
That's what makes this all so exciting. There's always more to learn, more to discover, more to wonder about. Thanks for taking us on this incredible journey through the quantum realm. We hope you enjoyed this deep dive into Bell's theorem and the EPR paradox.
It was my pleasure. And remember, if you want to delve deeper into this topic, we've got some great resources linked in the show notes. Check them out.
Until next time, keep those minds curious, keep exploring, and never stop asking those big questions about the universe.